There are 8 million people in the city. And in each and every one of them, there are 8 million times that number of living cells. Around 60 million cells in the human body. So it might seem a bit strange to compare something as small as a cell with something as large as a city. But in fact, it's not quite as perverse as you might think. Stroll around any city and there's certain things you'd expect to see. Buildings where people live, or ones where they work and produce goods. A power station to produce electricity. Markets where people shop. Roads, railways, bridges, perhaps even a river. All part of a complex transportation network to carry goods and people round the city. Now, on a quite different scale, a cell also has a number of structures with particular functions. For example, chloroplasts, a plant cell's solar panels. Or the nucleus, where genetic information is stored, a sort of cellular library or town planning office. Like all analogies, this one between cell and city must be treated with caution. We mustn't read too much into it. But it can be very useful. Just imagine you were a Martian in outer space, looking at a city on the surface of the Earth, and trying to find out what this object actually was, and what, if anything, a city did. How would you set about this? Well, arguably, if you're an intelligent Martian, the first thing you might try and do is build up a picture of the structure in as much detail as possible. Work out the different components of the structure, in other words, the city, and what the relationship is between these various components, how they sit vis-a-vis each other. And having done that, you might try and find some sign of activity, visually, sound, smell, whatever senses a Martian has, and then try and tie together these signs of activity with the various structures in the city. Now, in some senses, where cells are concerned, we're just like a Martian. Okay, we haven't just arrived. We've been looking at cells for at least 100 years. But the basic approach is much the same as that we recommend for the intelligent Martian. And what we hope to do in these 6 programs is to try and find out as much as possible about the detailed structure of cells, what cells contain. And then try to tie together these structures with activities that we know that cells as a whole perform. We'll look at the variety of techniques designed to do just that. Fine so far, but where do we begin? Well, we can't literally stroll round the cell, as we might round a city, because scale is against us. But what we can do is use our eyes, and in this case, extend our vision with the use of microscopes.
There's a whole variety of types of microscopy giving you a variety of images. But ironically, to see detailed structures within cells, we often have to kill them first. When we do this, we fix them to stop them degrading. A tissue, as it comes out of an organism, is too thick often for light to shine through, so thin sections are necessary. To be able to cut very thin slices, you have to support what you're cutting, so they are normally embedded in wax. The structures inside cells are transparent and colourless, so you need to differentially stain cells to bring up contrast to distinguish one from the other. We can demonstrate some typical techniques in preparing specimens for light microscopy. This kidney has been removed from a rat and rapidly fixed in 10% formalin. To embed it in wax, we must first remove the water from the tissue by passing it through an ascending series of alcohols. Finally, into a wax solvent, xylene. The kidney is then put into molten wax. This is put into an oven to keep the wax molten. The air is then removed from the oven because left under vacuum, the molten wax more easily infiltrates the tissues within the body of the kidney. After a few hours, the sample is removed and put into a mould, which is further filled with molten wax. The wax is left to set. The block is tipped out of the mould and sealed onto a wooden block, just like fixing a candle in a holder. The block can be trimmed first and then placed in a device called a microtome, which amounts to a very fine bacon slicer, allowing thin slices of kidney and wax to be shaved off as a ribbon. To get these onto a microscope slide, the fine slices are floated on the surface of water, and the microscope slide is placed underneath to pick up a slice. By putting the whole thing on a hot plate, the wax can be melted away, leaving the fine section of kidney attached to the slide and ready for staining. The slide and specimen is once again taken through a series of alcohols. This done, the slide and specimen is placed in the first of the stains, hematoxylin. It's then put into tap water, removing any surplus stain. It's then put in the second stain, eosin. A thin square of glass, called a cover slip, is placed over the specimen, together with an adhesive to keep the specimen in place. Everything's now ready to examine the specimen. The slide is placed on the stage of the microscope. A suitable field of view and magnification are selected. By this double staining technique, the hematoxylin picks out the nuclei in blue, whereas the eosin stains the cytoplasm pink. That's how you can get an image, but how can you interpret what you're seeing?
You're out in space and you're rapidly approaching Earth, and your instruments are trained on a city, and you're just picking up an object you've never seen before. Nothing like it on Mars. In fact, it's a house. But you don't know that. Are you sure you're in focus? Okay, now focus your attention on just the object you're interested in. So ignore, or better still get rid of, all extraneous junk.
But what is extraneous? Say you see this. If you've never seen a house, then you've never seen a car. So where does the house end and the car begin? And is this a house? Or this? Are they different views of the same house? Two different houses? Or quite fundamentally different objects? And what about this? And is this a house, or part of one? Can you, in fact, reconstruct a three-dimensional picture in your mind without actually having walked round the object? And do Martian telescopes, or Martian eyes for that matter, see in the human visible range, or in the X-ray or ultraviolet range? And what would things look like then? Perhaps you have to spray the object, to stain it, to bring it into the Martian visible range. And by this time, are you really sure that you're seeing and describing a real object and not just an artifact? Something produced by your Martian techniques.
So even describing something unfamiliar, like a house, might be much more difficult than the Martian anticipated. Well, when it comes to living cells, when we try and interpret the images we get down microscopes, we've got a similar set of problems. And the history of the Golgi makes that only too clear.
Camillo Golgi was born in 1843 in Corteno, near the historic city of Pavia, where he studied medicine and where he spent virtually the whole of his working life. Golgi was interested in uncovering the structure of the nervous system. And to this end, he invented a new staining technique: hardening tissue with bichromate and staining with silver nitrate. And this allowed him to pick up individual nerve cells and the many fine connections between cells to be found in nerve networks. But in 1898, perhaps seeking the font of all wisdom, Golgi applied his technique to the brain of an owl. What he in fact found within the Purkinje cells of the brain, seen here, was a fine network, his apparato reticulare, reticular apparatus. Well, this wasn't confined to the brain of an owl. For example, in these cells, seen here, similar structures existed. But were they real? Sure enough, you could find such things in other cells, not just nerve cells. But they didn't always look the same. So were they really always the same thing? And not everyone could find such structures at all. It all seemed to depend very much on the staining technique. So inevitably, the question arose, did the reticular apparatus exist, or was it an artifact of staining techniques? Well, Golgi's fame was already well assured by his elegant work on the nervous system, for which he was awarded the Nobel Prize in 1906. So famous that when he died, they renamed his birthplace Corteno Golgi. But ironically, the thing with which we most directly associate his name today, his reticular apparatus, what we now call the Golgi apparatus, or quite simply the Golgi, remained controversial well beyond his death in 1926. We spoke to Cambridge biochemist Professor Donald Northcott.
When I started, it was about 1950. And at that time, the only thing you could really use was the optical microscope. And the optical microscope was being used, and there was very little actual observation of organelles and what was inside the cell. So that the things you saw were specks, really, and these were labeled Golgi apparatus on the understanding of Golgi's work, in which he'd stained with silver. But they're at the limits of optical microscopy, about 1 mu. And so that the idea of an organelle was in great doubt, an actual thing in the cell which had a definite function and which had a definite shape and structure. And this was true of any organelle in the cell except the nucleus, really.
The problem with the optical microscope is you're on the limits of resolution. One way of improving this is to shorten the wavelength of the light. In fact, go from visible light to a beam of electrons. This was possible using the electron microscope. This is a modern electron microscope being loaded with a specimen. The specimen, this time on a metal grid, is placed in a holder which is inserted into the electron microscope. The air is then evacuated by pumping it out, allowing electrons to travel through the vacuum. The beam of electrons hitting the specimen produces an image which can be translated into our visible range as seen here on this monitor. This is a modern microscope, but were things always that easy?
One of the first microscopes in England was a Siemens microscope taken from Germany at the end of the war. from laboratories in Hamburg, shipped to, I think, Portsmouth or one port, and then since the Admiralty couldn't use it, they shipped it to a university, my university, Cambridge, where it was in fact assembled by the Cavendish laboratories, and then it was capable of being used. The difficulties with the microscope were immense. The power unit was put as a big bathtub on the top of the microscope. The thing took about 2 hours to pump down. You only took one plate at a time, so you had to be really certain that the picture you were looking at was worth taking. You took the picture, and then you took the plate out, and then you put a new plate in, and then you had to pump down for 2 or 3 hours to get the vacuum before you could start again. So it was a lengthy process. Now, of course, you take 24 plates, you put them in, you reel them off, 24 plates, you just put another cassette in, and it takes about 10 minutes or 5 minutes in a good microscope to pump it down again, and you're away. So it's very different.
But before you could even use the microscope, as with today's microscope, you needed a decent specimen.
In the 50s, the only way you could look at an object in the electron microscope was a solid object which you shadowed with platinum. And you put it on a grid, and you looked at it, and all you saw was the surface view. What people wanted were thin sections, as they did with optical microscopy. And that had to depend, really, upon the embedding techniques and the fixation techniques. The real breakthrough came with the embedding techniques. Before, we used to try and cut sections with paraffin, or as in optical microscopy. And the idea was that you would use swift blades. You cut very, very fast. So we set up razor blades on a revolving wheel and spun it at very high speeds to cut these paraffin sections. It was said that if you cut very fast, you get very thin sections. You see, the idea was to get thin sections because the electrons won't penetrate through a solid object. In the end, somebody thought of the idea of putting it into araldite and then polymerizing the araldite, and then you had a hard, solid object. And then how did you cut it? You cut it with glass knives. You threw a bit of glass on the floor, picked out an edge which was in fact sharp, set it up in a microtome, and cut the section.
The specimen is placed in a holder and screwed in position, ready for cutting on the microtome. But before this, the araldite is trimmed away with a razor blade. Nowadays, you don't have to throw glass on the floor to get a sharp edge. You can accurately produce glass knives or use a diamond edge as seen here. In front of the diamond edge is a trough which is filled with water ready to receive the very fine sections possible with this precise microtome. The fine sections are picked off onto tiny grids made of copper and palladium, the electron microscope equivalent of the light microscope glass slide. The specimens on the grids are now ready for staining. In this case, the stains have to absorb not visible light like hematoxylin and eosin, but electrons. A common procedure is to use heavy metal salts. The specimens are placed in an automatic staining machine where they will be successively stained with lead and uranium at a controlled temperature and for a set time. The specimens are now ready for examination. The grids are put into the specimen holder and held in place and fed into the microscope. With electron microscopy, it was possible to get clear pictures of the Golgi. Did this immediately settle the matter?
there are two difficulties with the electron microscope. The actual formation of artifacts and the interpretation of the image. If I take them in order, the artifacts, first of all. The artifacts are obviously you get material, you fix it, you dehydrate it, you embed it, and then you cut it. All sorts of things can happen to the cell, especially during the fixation and dehydration. So it's essential, really, to approach the object from 2 or 3 different methods in order to interpret your final image to make sure you're not looking at an artifact. But artifacts are not peculiar to the electron microscope. Artifacts are brought about in any scientific work. You prod something, you alter it. So that although it's emphasized a lot in electron microscopy, it's not really peculiar to electron microscopy. Nevertheless, you have to be careful by approaching the thing from several different points of view. Now, the interpretation of the image interpretation, you are interpreting a two-dimensional, essentially a two-dimensional image you have to interpret in 3 dimensions. You can cut sections at different angles, which will give you the thing cut in perpendicular or horizontal, and then it needs imagination to fit these images together to give you the total 3-dimensional object which you're actually looking at.
And this is the sort of 3D image we now have of the Golgi.
Thanks in large part to the beautiful work using the electron microscope, nowadays no one is in any doubt that the Golgi does indeed exist. And not only do we know that it exists in virtually all eukaryote cells, but we also know that it's a very interesting and important organelle. It seems that the Golgi is involved in putting the final touches to newly synthesized proteins. In the Golgi, carbohydrate side chains are added to the polypeptide chains. And it seems that this helps address the proteins ready for dispatch round the cell to their final destinations, or in some cases for export to the world outside the cell. But that raises a quite separate question. How do we know what the Golgi does? For that matter, how do we know what any organelle, any cellular structure does? After all, the Martian might build up a detailed description of a house, but would that description in itself tell the Martian that the structure was a building, let alone one where people lived? Well, that's the Martian's problem. Our problem is to attach function to cellular structure.